Hello and welcome back to Calculus 2 for one last time. Yes, tonight is the last lecture. We're talking about calculus in polar coordinates, and we are going to look into the formulas for differentiation and then integrals to find area of various shapes that we can get from functions in polar coordinates. So we will start first with noting that the polar coordinates conversion x equals r cosine theta and y equals r sine theta are two formulas that would fuel the conversion. And we will also know that r is equal f of theta, so that you can think of this r as a function if you have to. So now, given that you can have these functions produce graphs, and you can use your eyes to see that there are tangent lines all over the place, that means that derivative needs to be defined in some way, so we can take the derivative and eventually find the tangent line that is measuring the change. So if you recall, y equals 4 sine 4 theta gave you the flower which had 4 petals like this, and that was at 4. So if you have this to go, whatever the number here is, it will stretch as much. Now this is still on y and x axis, and you can pick a point somewhere, say here, and that will produce a tangent line, which means that that tangent line will have a slope that was dy over dx computed at whatever xy point that was, which you can convert from r theta, which you can also easily find. So my question is, what is the formula that calculates the derivative? And I would like to have that formula obviously in terms of r and theta, because I would like to plug in r and theta and be done. We saw last time that converting these polar functions into Cartesian functions is a living nightmare when you get it, and taking derivative of that would be even worse than trying to solve for anything. Will be implicit differentiation like to the 100th power. So yeah, we're trying to see if we can do this a little bit easier. So what am I looking for? I'm looking for dy dx, but I'm looking for that dy dx in terms of r and theta, which means that I'm going to write this as dy over d theta over dx over d theta, right? Because these d thetas eventually cancel and you just get dy dx. And now I need to take these derivatives. Well, bear with me because we need a longer line for that. I will write here again that x is r cosine theta and y is r sine theta. Keep in mind that r is a function, so r is f of theta. So what do I get to do here? Well, it's r times sine theta. That's a product rule, right? So as I am differentiating to find dy d theta, I have to differentiate that in terms of theta. It's a product rule. So copy the first one, which is r. I'll write f of theta instead, times the derivative of sine, which is cosine theta, plus copy the second, which is sine theta, and then you have f prime of theta. Go now do dx over d theta, again product rule, so copy the first one, which is f of theta, that's your r. And then derivative of cosine is negative sine plus copy cosine theta and then f of f prime of theta, right, when you differentiate that. And now we are going to actually write this so the derivative dy dx would be given as, and since the negative sign there, right, I'm going to put those as a second term, so I'm going to start with f primes first. So I'll go f prime of theta sine theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. I'm not sure if you want to memorize this or not, but you know what? It's there for you. You can derive it every time you need it, which is not that often. So say you have your r equal to 4 sine 4 theta, and you want the tangent line at theta equals to, let's say, 5 pi over 4. So for 5 pi over 4, the r will be 4 because that's, well, okay, we'll see what it is. So first I want to compute r. R is equal to 4 sine 4 times 5 pi over 4. Oh, I'm not happy with this one. Let's go 5 pi over 2. No, over 8. No, I'm just kidding. No, this is just for you who are using pens. Oh, you're not even writing it because I am? I see. So 4 and 8 will cancel, and you will end up with 4 times sine of 5 pi over 2. Now 5 pi over 2 is the same as pi over 2, so 1 is equal to 4. There we go. I hope this makes sense. So now I have the point 5 pi over 8 comma 4. That's my theta and, oh, r theta. Oops, 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 oops. So r and theta. There you go. Cool. What is the derivative dy dx? Well, all we need to do is to plug all of these values in. I need the derivative. So let me find that first. Just scribble it out. Did you just say Turks? Nothing. That was awesome. That's why I said he did. We all know he would never. I know. So we have from here that function is 4 sine 4 theta. That means that the derivative is equal to the derivative of sine is cosine. So you have 16 because of the chain rule, cosine 4 theta. And now we plug all of that in our dy dx is equal to 16 cosine 4 theta times sine theta plus function, which is 4 sine theta times cosine theta, everything divided by 16. That's what I said. It's clearly 4 sine. You need me to zoom in? It's right here. It says 4 theta. Thank you. What was I talking about? 16 cosine and then cosine theta. There we go. Minus 4 sine 4 theta sine theta. Awesome. Theta is 5 pi over 8. You can plug everywhere. So don't be angry. 16 cosine 5 pi over 2 sine. Oh, great. We're going to compute this now. Plus 4 sine 5 pi over 8. Cosine 5 pi over 8 divided by 16 cosine 4 times, well, actually I could just write 5 pi over 2. So over here I'm just going to do that. Sine 5 pi over 8 plus minus 4 sine 5 pi over 2.
Why is it sine 5 pi over 8?
Sine
Because that's
pi 5 pi over.
No, I meant in the first term of the denominator, why is it 16 cosine pi?
Oh yeah.
Sine 5 pi.
16.
That's the derivative times cosine, right? So here's your derivative times, this is a cosine here, right?
Yeah.
Is that what I'm hearing?
Yeah.
Thank you. Thank you. Now,
Why does it keep switching from 8 to 2 on the cosine side?
because these ones had 4s,
Oh, okay.
so they'll cancel, right? And then somewhere they cancel, somewhere they don't. Such is life. All right, so all of these, what is this 58 over? All right. Good. So now, sine of 5 pi over 2, so it's a 4 right there. So we get to compute all of these, right? Well, cosine is 0. So this one is 0, right? And cosine is also 0 here. But there should be sine, right? So we have that these two are both zeros, right? Because at every pi over 2, cosine is 0. So that's out, the whole term. We are left with the terms on the left. And for the terms of the left, signs cancel, right? Do they? -1. So now you are left with sine will cancel with the sine, and 4 will cancel with the 4, and you get negative cotangent of 5 pi over 8, which is equal to a number which is a slope, right? So this is calculation for slope. This is calculation for the slope. Once you plug in numbers, right, you get the slope. So there's your m. And then you have your point, which you can transfer back into x and a y, and you can find the rest. Done deal. Integration. Are we good?
I like this one. This one just looks like
All right. For integration, I'm going to erase this title actually first, because let's review solving the trigonometric equations first, because that's a major skill which you guys need in order to survive integration portion. And then we're going to do integration. So trig equations review. This is just quick. We'll do 2 and it's enough. So first of all, let's say you have 2 cosine x plus 1 equal to 0. Let's say this is the trigonometric equation which you are considering. You know, the greatest time you walk in a classroom, those are the first words you hear. Trigonometric equations you want to consider. And to solve this, you leave cosine alone, and you have negative 1/2 on the right-hand side now. There are a few ways in which you can solve this. One involves you memorizing the unit circle or memorizing values. What I like to do is I like to graph this to know without thinking too much which values do I need to worry about. So if this is the cosine, I know it tapes down through pi over 2 or 3 pi over 2. Again, whatever method you know, I don't care. Use whatever you want. I know this is negative 1. I need negative 1/2. Negative 1/2 is here. So there I say clearly, intersection is here. This is going to be my x1 solution. And then another one over here, x2. The hell, I can't write x. X. That's a v. X. There we go. Much better. So now I know that the cosine and a half is produced at pi over 3. So this better be 2 pi over 3 and 4 pi over 3. So that's how I solve equations. Because all it is, to solve any type of equation in the galaxy, it's always graph the left-hand side, graph the right-hand side. You graph both of those, and you will get solution.
How did you know it was 2 pi?
Because I know that cosine of pi over 3 gives me 1/2. And that means that everywhere on the unit circle at this 4 location, cosine is a half or a negative half at these locations. So the pi over 3 is here, 2 pi, 3 pi, 4 pi, and the 5 pi. They're all there. So had to be some of those. Let's say you have 2 sine x is equal to sine 2x. I don't know. Is this going to be a nice one? Maybe. Maybe not. How do you solve this type of a problem? Well, you move this to the other side. You get sine 2x minus 2 sine x equal to 0. Then you use trigonometric identity 2 sine x cosine x minus 2 sine x equal to 0. And then you factor 2 sine x to get cosine x minus 1 equal to 0. From here, 2 sine x is equal to 0, and cosine x equals to 1. Graphs will suffice here. If I am on 2 pi, here are my 3 solutions. On 0 to 2 pi, x is 0, and pi and 2 pi. And for the cosine side, cosine is 1 at 0, which is a repeat solution, and 2 pi, which is also a repeat solution. So what is the solution set? 0, pi, 2 pi. 3 answers for this particular set. So I have a way to systematically solve. I like to draw graphs, but if you are, if you are in love with unit circle, please use that. Whatever makes you happy. That's the important part, to be happy in calculus while you're solving equations. So now, let's take a look at our calculations for area in polar coordinates. So I will remind you that for x and a y in rectangular coordinates, your area is computed when you have a to b f of x dx. That's how you find the area integral in rectangular coordinates. You do that and you're good to go. Here's the accompanying graph. You have some kind of function between a and b. This is what you're talking about. So not that bad. But now when you move to r theta, the formula changes. The formula is going to be 1/2 integral alpha to beta of f of theta squared d theta. Derivation for this is in the textbook, but I'm still going to talk about it a little bit so we understand. First of all, now the input variable is no longer x, obviously, it's theta. What you used to have as a representative rectangle, dx, which you guys will use 10 times more in your Calc 3 class. Now you have a representative pizza slice, d theta. So if I have some kind of a curve, and here is the center, this is your representative rectangle. I call it representative pizza slice, d theta. That's the one that computes areas. And as you can see, that d theta goes from alpha to beta, which are angles. Angles theta 1 and theta 2. So now I would first, and I should actually box this formula because this is it. This is what you must know. Going into Calculus 3, you are taking this formula and upgrading it to cylindrical and spherical coordinates in chapter 13. So you have to know polar coordinates in order to be able to go a step higher, one more dimension up. So what is happening here? First of all, dimensionally, we should know that area is 2D, right? And you know that there is multiplication between f function squared and d theta. Well, d theta is not giving us a dimension this time around. You see the function squared, so 2 dimensions are right there. And if d theta was a dimension, then you would have 3D, so this would be volume. But you have to understand that theta is not length. Theta is an angle. And that doesn't have a spatial dimension assigned to it, because you turn angles in the already existing 2D space, which is defined through x and a y. So the d theta over there does not contribute dimensionally to the equation. Both dimensions come from the function squared. Another way that you might want to consider to understand why theta has no dimension to it is, even though there are units like, you know, inches or degrees, is that the way the radian, right, which is the unit for the theta, is defined. If you know in the unit circle, 1 radian, right, 1 radian is the ratio of the arc length and the radius. So when you divide those two, so theta, which is 1 radian in this case, is equal to, when you take s and you divide that by r. Now look at that. If s is measured in inches and radius is measured in inches, they cancel completely, and theta has no units in terms of length. We call it radians because that is the way to divide the unit circle. But you can also have a unit circle divided into 360 pizza slices, where one of those pizza slices is called 1 degree. They're not lengths. They don't have a unit for length associated, which is the reason why d theta doesn't carry dimension to it. Therefore, both dimensions come from here, and therefore you have the area on the other end. Where in your previous case, right, your previous case for these guys, this was the length and this was the height, so height times the length is giving you the rectangle, which is the area. So now it's a little bit different. There are also derivations. Why is the 1/2 there? Well, some integrals and some stuff, and you know, when you integrate f of theta, well, actually when you integrate r dr, you get r squared divided by 2, and then you write this r as f of theta. So if you're interested in these derivations, please take a look at the textbook. They will be explained there, or see me during office hours, or after the finals, or over summer, right? It's fine. So now what I'm going to do is I'm going to first prove the area of the circle, the formula for that, because you never know when you're gonna tutor someone who's like, you know, 5 or 7, and they ask you why. This is why. So you want to show that the area of this circle with radius capital R is what? Pi r squared. So a kid asks you why. You say, well, obviously, you have 1/2 integral. You want the entire circle, so you will go from 0 to 2 pi, because it's the full circle, 0 to 2 pi. And then your function is just r squared d theta, right? Because the only thing that you are I hope you're remembering that the equation for the circle is r equals to a number. Now I'm just calling that capital R because I want every number to be represented. You also know that f of theta is equal to r, which means it's big R. And then when you plug that f of theta, which is capital R, into the equation, you get r squared, right? So all of that stuff. So now when you integrate this, you get 1/2 r squared theta. You are integrating in terms of theta, so don't go r cubed. You're not integrating in terms of r. You're integrating in terms of theta. So r squared, you copy that thing. And then the integral of d theta there, because there are no other thetas, is just theta, computed from 0 to 2 pi. And now you plug that in, you get 1/2 times 2 pi times r squared minus 0, who cares? And there's your pi r squared, which is what Greeks knew before time was invented. But you know what I want to know? I want to know what I want to know is, what is the surface area of 3 slices of large 12-inch pizza, because I want to optimize, the amount of toppings and all of that stuff. I want it to look good to be covered, but I also want to save money, right? As a business owner. So what is the area? What is the area for 3 slices of large 12-ounce pizza? Now, how many slices it's cut? So that's where you start. You draw a 12-inch pizza. Great. What's the radius? Radius is 6 inches, right? So if radius is 6, you have r equals 6. That's your function. So f of theta is equal to 6. Great. Now, 3 slices. Where do we start? You cut the pizza. And then you say, all right, so 3 slices. Let's shade 3 slices. By the way, if the pizza is green, don't eat it. This is just to represent it here on the... Unless it's pizza with broccoli, then eat it. But that's a different type of a slice. Anyway. So now I have these 3 slices. Can you please let me know what alpha and beta are? Use your eyes and let me know. What are the alpha and beta? Very good. This is the stuff that you have to know. Otherwise, you don't get to set up your integrals. So area is 1/2 integral 0 to 3 pi over 4 of 6 squared d theta. 6 squared is 36 divided by 2 is 18. So it's your 18 theta from 0 to 3 pi over 4. Which is further equal to what? What is it equal to? 9 times 3, 27 pi over 2. Right? Right. Now, obviously, when you are in a business of pizza, you will say pi is 3. You don't have to go 0.14, who cares? So then you would have 27, was actually 30 times 3 divided by 2. 15 times 3, 45 inches squared. And then you figure out how much ham slices are, mushroom pieces. Do you think that anyone does that? No? There we go. You have a little private pizzeria. They don't, right? But they don't have a chain that has, maybe 1,500 stores where the stuff gets moved in those huge bulks. Because if you get to save $1 a day per store, right, times 1,500 stores, times 30 days in a month, right, times 12 months, right, or 365, whatever you want to. Exactly. You see, that's huge savings. So, no one cares. You have a little chocolate factory or something at home, that you're doing for yourself. Sure, as long as you're floating on top, you're good to go. But in a corporate setting, every mushroom is counted. Like, okay, 1, 2, 3, you get to put 17.5 mushrooms on this pizza over here. And if you don't do it as the employee, well, we'll find the one who will. That's how it goes. And some of you work those chains, you know. Great. So we found this. The next order of business is I want to know what is the area of one petal of a flower given by r equals 3 cosine of 2 theta? Sounds good enough. All right, so now, you know what? I see some of you are reaching for the calculator right now because you got to graph this thing, right? Well, we're going to graph this by hand. Because even if you graph it on the calculator, still have no clue, theta-wise, where a petal begins and where it ends. One of them. And that could be a problem. Because you don't know your alpha and beta. So even if you have the picture in front of you, it tells you nothing. It used to be good because your function and it was between A and B and you see it. But my question now is, if I draw a flower, which one of these was drawn first? Right? Or if the flower looks like this, right? Does it start in the middle and then go around, and which way goes around? Does it start at the end and goes this way first into a propeller of some sort? It starts here and then goes there and then goes there and then goes there, and then which way does it go? Right? We don't know. So the best way to do this is actually to graph it yourself and see. So you start this by picking your thetas, which will tell you what r is, and then you have your r comma theta to graph on the graph. Now, since this is a 3, your graph should have 3 units each way. That's how much space you need on your xy graph. It's very simple. So you're clearly picking theta equals 0 first. You plug that in. Cosine of 0 is 1, so you got r is 3. You have 3, 0. You see that we are starting here. That's where radius is 3 and theta is equal to 0. And then you say, all right, what else is the cool value that I can compute? Well, it's pi over 6. But pi over 6 and cancel it 2 is pi over 3, so you can actually do better than pi over 6. You can do pi over 12. Because when you put pi over 12, when you substitute pi over 12, it becomes pi over 6. And you can compute that. So how much is, if you put pi over 12, then how much is cosine of pi over 6? Very good. So that's 3 root 3 over 2 altogether. Now, how much is 3 root 3 over 2? Well, root 3 is 1.7, right? So you see that, and pi over 12 is here, so it looks like it's right there. Then you move to pi over 6. Pi over 6 is actually pi over 3. When we plug it in, it's a half, so it's going to be over here. So 3 halves. Pi over 6. So then you have your pi over, oh, you can do also pi over 8. So pi over 4. What's pi over 4 going to do for us? Pi over 4 is going to give a 0? Yes. So you see that we got half of a petal. We started at theta equal 0, and over here we ended with theta equal pi over 4. And that gives you half a petal. Can't we just be creative and say double half a petal? Right? That should make sense, right? Do what?
Does it though? Like, symmetrically speaking, I get that it makes sense, but is that how it always turns out?
In Calc 2, yep. In Calc 3, it won't. But in Calc 2, yes. So what I can do now is I can say that one petal, well, area of one petal will be 2 times 1/2 integral 0 to pi over 4 of my 3 cosine 2 theta squared d theta. These die in front. I still have 3 squared, that's 9. So this is equal to 9 integral 0 to pi over 4. Oh, look at this beautiful thing. I have to integrate cosine squared. How do we do that? Yep. Power reducing formula. So 9/2 integral open parenthesis 1 plus cosine of what? 4 theta d theta. Nice. Because you have to double the angle. So that's 9/2 integral of 1, that's theta. And then what's happening with the cosine over here? Cosine goes into sine with the 1/4 in front. From 0 to pi over 4. You clearly see that sine dies because sine of pi over 4 times 4 is sine of pi. Sine is always 0 at 0, pi, 2 pi, 3 pi. So sine will drop, and all you get is 9 over 2 times pi over 4, which is 9 pi over 8. And you got the area of one petal. Since the original problem was cosine of 2 theta, that means it had 4 petals. You can multiply this by 4 to find the area of the entire flower, if you want to. Yes?
When we multiply by 4, we have to change the outcome. Does it remain the same?
When we multiply,
Like no. When we found from 0 to pi by 4 was this half each other.
Yes.
So we need the other half.
Yeah, you can just multiply by 2.
So do we have to do anything with the outcome?
No. The reason why is you're not using substitution. Now, what you can do, and I'm going to show this, is what I did is I utilized the theorem from Calculus2, which said that the even function on a symmetric interval can be done as 2 times half of the interval, so 0 to a. Instead of negative a to a, you can go 0 to a. That was the theorem in 5.3, I believe, or something like that, in Calc 1. And you do have theta, sorry, you have f squared, well, squared, that's even. So that's why it works. Now, the way without cheating would be to keep computing and realize that you are going to, well, now I know when I started with the graph, now I know exactly how this how the whole graph is going to be drawn. So here, we are starting here, and the calculation did this. The next part where the graph is going to go as you push past pi over 4 is going to go this way. And then it's going to complete this petal and push it here. And then it's going to complete this petal and push it here. And then it's going to complete this petal and then push it finally at the end. You see? So that's the sequence in which it would draw. Now, what you can do is you either do what I did, which is you compute half of the petal and then multiply it by 2, because that will be common sense, because it's symmetric. But you also know that this is 0, alpha equals 0, it starts there. Let me just call it theta equals 0. So theta equals 0, and you know that this point here was theta equals to pi over 4. So if you are to draw the bottom part of this petal right here, that means that this is negative pi over 4. See that? So you could have done this, right, over 4, and then you have your whatever the hell was 3 cosine theta everything squared d theta, right? So, but then if you use the theorem from Calc 1, you see how all of mathematics kind of clicks in. If you use the theorem from Calc 1, it says double the original integral and then cut the interval in 4. And this is exactly what I had here just by using the symmetry, saying that we can exploit that.
Where did you get that 1/2 on that system? I see where you got the 2 rounds. Oh.
Excellent. Great. So I hope you understand a little bit of how this goes, because we are about to make it much worse. Design calls for a circle interlapping somehow with the flower, right? So what is the area of one of those intersection pieces? So those are the scary problems, which is the stuff you're going to see in your engineering. So say you have that's terrible. Say you have your previous r equals 3 cosine 2 theta flower, and you are intersecting that with a circle which is just 2. Well, that will be this. There's a graph. And then someone comes along and says, I want to know what this is. Like that much. Or, I want to know how much this is. Or this one over here. I know. Now, you know what? If you know how to find one of them, you know how to find all of them. What makes this hard is the new way of thinking that needs to be developed. You are now moving and the radius swiping from alpha to beta. You have now representative pizza slice to worry about. So let's say you want this piece over here. Let me draw that piece larger. So there is a circle on this side, and then there is a petal poking out of that circle. There is this x-axis coming this way, and there's the circle. So this is the area you want to know. You already know that you are going to compute a half and then go times 2 because the second half, right? You know that both circle and your graph start drawing here at theta equal to 0, but now you have this mysterious intersection point here. That you have to figure out the value for. And what would that intersection point be? And how would you find that one? Nope.
But when we look at the other side, it is from the
It's theta. What's the value of it? I'm not asking how far is from the origin. Sure, it's a radius of the circle, which is 2. What is the theta? Because we know that this point here is theta equals 0, right? That where it starts. What is the point here?
It is the length of half the petal.
Huh?
This solve for the, again, you solve for the trig problem here.
Yes. Now we get to solve trigonometric equation to figure this out. And trigonometric equations for these points could be really nasty. So now I have to equal 3 cosine 2 theta to 2 and somehow solve this monstrosity. Now obviously these are not going to be any kind of nice numbers because I just threw out whatever, right? Functions. But you see that applying inverse cosine to both sides gets you that 2 theta is equal to inverse cosine of 2/3. And then you will make sure you stay in radians when you do this calculation in your abacus. So first you go mode, make sure you're in radian. And then you say inverse cosine of 2/3, which gives you 0.841, and you will divide that by 2 to get that theta is equal to 0.42 is fine, okay? Radians. You don't get that in terms of pi because I didn't bother figuring things out. Okay, so now I know that this is starting at theta equals 0, which is your alpha, and it's going to end here at beta. Now, I want you to observe my representative pizza slice. It's gonna stretch from whatever this, it's gonna stretch from whatever the center is, and I'm going to draw, I'm gonna remove this half area. I'm going to draw a dashed line like this, and then here I'm gonna go solid. And then it's representative pizza slice, so here we go. And I'm going to color this and call it d theta. This is extremely important Because remember, you are now between two functions and the same rules apply like for the 6.2. See how we complete the circle in this class? We start with area between two curves, we end the same course area between two curves with all the horrors that were in between, like sequences and series. So now when I'm setting up my integral, I know that I will be calculating half of the area, so area must be 2 times 1/2 integral from 0 to 0.41 or 2, whatever the hell was, 42. And now you have right minus left. Oh, I don't have room here, so let me go down. So area is going to be 2 times 1/2 integral 0 to 0.42. Now, representative rectangle on the far end, or pizza slice in this case, is touching the flower. So that's going to be 3 minus cosine 2 theta minus the inner integral, which is just 2 squared. Why do I have minus here? It's just 3 times cosine. All of that d theta. And then you compute from there. These guys will cancel. I have the integral 0 to 0.42. That's a 9 cosine squared 2 theta minus 4, all of that d theta. Then you have power reducing. And then here, just do it. I mean, this is your regular trig integral from 7.3, so you might want to practice that for final. You know what I mean? You go home and you crank a few of these. Isn't this fun? No way to ruin the mood. Shall we take 5 and then talk about the exam? Or you want to do one more of these integration interesting problems? Break?
Break, do one more, and then exam talk.
I'm streaming now. If there is a break, I'm stopping streaming and there's no more problems. One more problem?
Yeah.
All right. Then the break, then
We're
stuff.
just gonna keep doing this.
Is that a book that I see over there? Oh,
Oh, this is my test. They're all majoring in dance. Maybe not here. The fairy dust? Doing tricks and dance. Ah man, you gotta go for
all right.
I can't do interpretive dance. It's about as like graceful as But this, I don't know, I do it weird. Yes. Is that gonna be my back? It's just one big wheel.
7. They're ahead.
When I was ahead,
They're 7.
Professor, you know, like cosine 2 theta. Well, earlier you had sine 2 theta. You took it out and you replaced it with sine theta to cosine theta. Can you do that with cosine, or that's like a no? You just can't. 12 hours back. You just got integrated with that one.
Because the other one is identity, right? But there's... Well, there is. It's called cosine squared minus sine squared. It's just worse. Yeah. All right, guys. Are you ready?
Yeah.
That's the spirit. Sheesh, I don't know which one to pick. What's the good number? 43. R equals 1 plus sine theta. And R equals 1 plus cosine theta. So try this on your own for about 17 seconds and then I'll kick in.
That's what I just said, but you can't do it.
I think he just wants us to find the points. You know math. You get anywhere? Get anywhere? Live streaming real fast.
Wait, see if you can rewind the live stream and see the bit where he did the thing.
He said, oh, I want that.
I'm gonna show you anyway, so
He said, oh, I want this one. He's like, I want this one. He didn't do it. He just went,
Can I see that, sir? Do we just have to find the outside data or the area?
The area.
Okay.
Yeah, the whole thing. Yeah, what happened? Same question? Glad you delegated, huh? All right, we're gonna start soon. Morning. How are you? Yeah. Good? You what? I'm concerned with everybody. It's okay, I don't mind.
Here's what it looks like on
All right. What happened?
Like, do you use yourself right?
Oh, yes. Not this year. No. Are you done? Would you like to show to everybody how? All right, guys. Let's focus on. Let's focus on this, so that we can eventually do work. All right. The shape that you are getting is called cardioid. Looks like a heart. So cardioid. And we have the other one. Trying to see. This is too wide. I gotta draw this again. It's too wide.
I guess the graph. Passing chairs, bro.
Was uncomfortable.
What happened to the peach?
It disappeared. So now let's see where the points of intersection here.
Oh, okay.
Where are the points of intersection? Yeah, there's a point intersection here. There's one over here and one over here. So there should be 3 points of intersection. So that's 1 plus sine theta is equal to 1 plus cosine theta. Ones will clearly drop immediately. Sine equals to a cosine.
Now is that cutting the streaming or is that cutting the
program? The stream controls the stream.
There should be, I think, 3.
How would we get 3? Yeah, because 5 or 5. Yeah.
Hang on.
Yeah, they're equal on the first and third quarter.
Yeah. If I have to draw this bigger, I'm going to draw it bigger and then see. For some reason, I think there are 3 intersections, but the equations give me 2. So I'm going to use maybe 2 units as 1, right there, right there. All right, so it would go like this. It will have this part going all the way to the top. So this is 1. So this one is the first one. And then you will have the same one except sideways. So it will have this. And it will have this. So see, this is the part where I...
Oh wait, hang on. There's wait. That's still only 2 intersections.
No, I think it intersects about 5 or 4 points. That happens
You see, so I think there's intersection here, and the origin, and then this one. You see those?
Yeah.
So I think there are 3 intersections, one over here, one at the origin, and one over here. So I think there are 3.
Professor.
Yes.
I graphed it, and the bit at the origin, they don't actually touch.
Oh yeah, but they don't touch at the origin, actually, you're right. Because if it's... Oh no, actually they could.
I don't think they do. I ran the trace function, and they don't. I mean, you could also Google it.
Yeah, maybe the calculator is... I don't know. Anyway.
And you only found two.
All right, so now we have to solve this, guys. So how do you solve this? You will divide both sides by cosine.
Well, it's 2 or 3.
2. And you get your tangent theta is equal to 1. Tangent theta is equal to 1 at pi over 4. And 5 pi over 4. Because all students take calculus. Tangent is positive in first and the third quadrant. So you have 1, 2, 3, 4, 5. So these are the two values. So this is your pi over 4. And this is your 5 pi over 4. Those are the intersection points. So they don't intersect here in the middle. Now the question is, which area do you want? So let's color this area here. Which actually leaks into this little piece there. And if I draw a representative pizza slice, ooh, I have to have two integrals in this case. Nice. Yeah, it's gonna be two different integrals here because the way it's cut, it goes 0 to pi over 4. No, it goes pi over 4 to 5 pi over 4. Yeah, it's much easier to compute one of these side things because that would be the difference between integrals. This one over here is tricky. This is your x-axis. This is the original one, right? So it will be original one, 0 to pi over 4, plus the sideways one. Okay, so this area would be the 1/2 0 to pi over 4 of the original one, which is 1 plus sine theta squared d theta plus 1/2 integral of pi over 4 to 5 pi over 4 of the other one, 1 plus cosine theta squared d theta. And then, yes. The problem is, so I'll draw a few shapes so it hopefully makes more sense. So let's say you have, again, let's go with the cardioid and a circle. It's always easier if you're using circle to understand things. And let's put the circle right here. So you have this intersection point and this intersection point here. You can call them alpha and beta. Those intersection points give us these rays, let's say, like this. So now you know that up to here is alpha and up to here is beta. Now the question is, which area do I want? Do I want the area in here, which is, let's say, this area here? Let's say this is something that we are looking for. So what do I do with this? I draw a representative pizza slice, and you see how the pizza slice hits here, which is the cardioid, and then the bottom of that is touching the circle. So area is going to be 1/2 integral cardioid squared minus circle squared d theta. Now what are the limits? The limits are not from alpha to beta, but from negative alpha to positive alpha, because they have this beta is also negative alpha at the same time. Observe that I want this part here. Now, if you want these pieces inside, you will have to use representative rectangle and then alpha to beta. So maybe I should let me just color code this and put this one that corresponds to green, okay? Now, let me draw the pink part here. That one is going to be circle minus cardioid. So 1/2 circle minus cardioid d theta, and the limits are alpha to beta. And that one is this one. And then you have the white one in between. So as you draw a representative rectangle here, you see that the representative rectangle goes all the way out to touch the circle, and then the inner one closer to the radius from where it originates is touching the cardioid, right? Now over here, the white part is really tricky because representative rectangle always sits at 0, and it's touching the circle until it gets to this point, and then it's touching the cardioid. So 3 integrals. It goes from 0, cardioid stops there, then it's going second integral for the circle loop, and then another one for this loop. So 3 integrals there. Because it's a little bit tricky to learn these things tonight. It takes a long time for these things to settle in. And what I would suggest you to try learn this is not with these things. I want you to go back to this and your representative rectangle, and it's f minus g. And then I want you to take a look at it this way and say, okay, so now this is f of y and g of y, so it's f minus g again. And then what are the other things that you can have? You can have a function like this, and a function like this, and a function like this. And now what happens? Well, for your dx, right, it's going to go f minus g, and then over here, plus, this is h minus g. So you have to kind of get used to this first. You have to be very proficient with these to understand that representative rectangle, top is touching f, bottom is touching g, so f minus g, and then when it presses this line, top touches h, bottom touches g, so h minus g. And only then you will be able to go here and say that the representative pizza slice, which always stretches from the origin towards these functions, representative pizza slice, this is the farthest out it can go. That's analogous to you're stretching all the way up to f, and then minus g, which is the inner. So this is the cardioid squared minus the circle squared for the green one. But then the limits, right? You can't go for the limits alpha to beta because alpha to beta covers this, and that's exactly what your green is not. You have to now understand that theta rotates. So you can't go 0 to alpha because 0 to alpha would cover only half of it. Well, you can, and then double it. But what happens if it's not symmetric, right? So you would have to go from negative alpha, which is right here, negative alpha through 0 to positive alpha, because if you are able to think of these red lines as like, you know, minute hand and hour hand on the clock, and they're doing that, right? Well, they're going from here, right, and doing that. Then you would be able to faster figure out where are the angles and so on. So only then, when you're proficient with that, you will start your representative rectangle at 0 here. Representative rectangle starts at 0, and you can see that from this intersection point here, which is alpha, from alpha all the way to beta of just a circle will give you the area of the circle, which is common sense, but it will give you the area of the circle up to here and up to there. I missed this red line. Red line should go through this intersection. So what you don't get included? You get all of the white except these two pieces. These two pieces will be this one over here, so you have to go further in. So from alpha to whatever this next intersection is, to fold in. So this one is 3 integrals. You have integral here, integral for everything there, and then another integral there. It kind of bothers me that I missed that thread, but such is life. It takes time to get used to this. What do we do in Calc 3? We take this and we upgrade that to cylindrical and spherical coordinates, which means that we add a third dimension to it. So this becomes your domain. And then you have to understand that in the domain, how it works. There it is. So this green blob on the bottom, that's the domain, which is the polar coordinates, and then you have the shape above. Now this was done in spherical coordinates. Sphere, conversions, and all of that good stuff. Here's the ball, right? Half of the barrel or whatever, and so on. So it gets upgraded. So please don't just go and say, all right, I gotta pass the final. So because if you don't learn it, then in Calc 3 you have to learn what we learned today so that you can upgrade it. That's, you know, that's something that you really have to pay attention to. All right, so that takes care of the of this one. Oops, didn't want to do that. Didn't want to stop this one.